Welcome to Pre-Calculus. Today we will investigate solving logarithmic equations. We'll take a look at 4 examples. Our first example is log base 6 of negative p equals log base 6 of negative 2p minus 3. When I have a logarithmic equation where there's log to the same base on each side, one strategy I can use to solve the equation is really to set the two arguments equal to each other. So definitely with this equation, I do notice that I've got log base 6 there on the left and log base 6 on the right. Since that structure is in place, in order to solve this equation, I'm just going to set negative p, the argument on the left logarithm, equal to negative 2p minus 3, the argument on the right one, and solve. That's going to be a simple linear equation. So I'll set it up negative p equals negative 2p minus 3. And to solve this equation, we can do it in one step by simply adding over 2p from the right. It'll cancel there. And add it to the left, negative p plus 2p is going to give us just p, and immediately we have a solution p equals negative 3. Our second example has only one logarithm. Here we've got log base 4 of n plus 10 plus 1 equals 5. Whenever you've got a logarithm on one side and just numbers either on the right side and like this plus 1 here, we want to start off by isolating the logarithm, by getting the logarithm base 4 in this case of n plus 10 by itself. So I'm going to start by subtracting the 1, the constant here on the left. It'll cancel on the left and then give me log base 4 of argument n plus 10 equals 4. Once I have it to where the logarithm is by itself on one side and it equals just a constant number on the other, I can convert this to an exponential equation to continue solving. Remember how that conversion works. I'm going to start with the base 4, and raise it to the power of the value on the far side of the equal sign. So my equation is going to start 4 to the power of 4 equals, and that's going to come back around to the left side to equal the argument n plus 10. Once I've converted it to an exponential equation like this one, I can continue solving. I do need to raise 4 to the power of 4. That's going to be a large value. So that's equivalent to 16 times 16. So we'll multiply here on the side. It's going to be 63. Too large. We'll start again. So 6 times 6, 36. That's going to be 9. And then 160. And when we add that up, that's going to give us 256. So here we've got 256 equals n plus 10. And we're just one step away from a solution. All we've got to do here is subtract 10 from the right and from the left to get our solution n equals 246. So with our first example, we had 2 logarithms. With this example, we had just 1 logarithm. Let's take a look at a third example that again involves 2 logarithms, but on the same side. Here I've got log base 4 of 8 minus log base 4 of x minus 1 equals 4. Whenever I've got logarithms of the same base, either added or subtracted to each other on one side, I can combine them into one logarithm using my logarithm properties. Recall that if I have this arrangement where I have log base 4 of 8 minus log base 4 of x minus 1, this minus is going to convert to division. So to combine these 2 logs on the left, I'm going to put log base 4 of the numerator 8 over denominator x minus 1. and that equals 4. Once I've combined my two log statements, in this case, they were a difference, so it converted to a quotient, I can again convert the whole logarithmic equation to an exponential. Again, 4 to the power of 4 is going to equal the argument 8 over x minus 1. We'll make the conversion here below. 4 to the 4th equals 8 over x minus 1. So we just saw 4 to the 4th power is 256 equals 8 over x minus 1. So at this point, I have to identify this as a rational equation. So recall, one strategy to solve a rational equation is to multiply both sides by the common denominator. Since only one of these sides has a denominator, that's what I'm going to multiply by. So I'm going to multiply on the right side by x minus 1, and that will be a cancellation. I'll also multiply the left side by the same factor. When I distribute 256 through that binomial x minus 1, I get 256x minus 256, and that equals 8. Then I've got just a simple linear equation. I'm going to add 256 over. It'll cancel on the left. And I'm going to add 256 plus 8 here on the right. And that'll give me 264 equals 256x on the left. To finalize the solution here, I'm going to divide by the coefficient 256. And that gives me x equals 264 over 256. And definitely we can reduce that fraction. Definitely both of those factors share, or those two numbers share a factor of 2. So let's divide out a 2. 264 divided in half is going to give us 132. So it looks like we could keep going with the division. 132 is also even, and that's going to give us 66. We can keep going. 66 is divisible by 2, and that's going to give us 33. So at that point, I can say that the factors of 264 are 2 to the power of 3, since I divided 3 of them out, so that's 8. And 33 itself is going to be 3 and 11. So to make the reduction, I know that 256 is 4 to the power of 4, so I can definitely divide it by 8. Let's divide 8 out of 256. And that's going to give us 32. We'll make that final formalization here. If I divide 8 out of both, I'm going to get 33 over 32. So that was an example of an equation where I combined logarithms that were presented in a difference. It converted to a quotient. Let's take a look at one last example that involves two logarithms that are a sum. Here I have log base 6 of 2 plus log base 6 of 4x squared equals 2. Again, I have two logarithms that have the same base on one side that are connected with either addition or subtraction, and I can convert them, in this case, because it's addition, to a product. This is going to become log base 6 of argument 2 times 4x squared. And that's going to equal 2. We'll simplify that product. That's log base 6 of 8x squared. And again, once I get the equation to where I have one logarithm equals a constant value, I can convert to an exponential to continue solving. That's going to be 6 to the power of 2. So that's 6 to the power of 2 equals the argument 8x squared. We'll continue solving here. So this is definitely going to be a quadratic equation. That's going to be 36 equals 8x squared. And then I want to divide, in fact, not divide, I want to take over 36 well, there's different strategies. I could subtract 36 and factor and then try to solve by factoring, but I do see that I could also solve this by using a square root. So I'm going to isolate this x squared by dividing by the coefficient 8. And that's going to give me 36 over 8. We can reduce 36 over 8 by dividing 4 out of both terms. So that's going to give us 9 over 2 equals x squared. And then to solve that equation, I just want to take the square root of each side. And that's going to give me a radical of the fraction on the left. So currently I've got x equals, so I can take the square root of 9, that's going to be 3. But I cannot take the square root of 2. So to get that answer in a rationalized form, I can't have that square root in the denominator. I want to multiply by the square root of 2 below and above. So our answer here is going to be x equals 3 times the square root of 2 over square root of 2 times itself is going to be just 2. And one thing we do need to remember is that this is going to be plus or minus. Remember, if I take the square root, it gives me both a positive and a negative version of the answer. And that completes this fourth and last example. So thank you for joining for this investigation of solving logarithmic equations. See you soon.